Now, I will explain the difficulty and WBB for non-flat structures. For example, in tunnel, physical compression direction is different from each element, and this direction cannot be determined by element geometry only, such as direction foci. The element geometry just provides two normal direction of the element. Thus, an additional condition is needed to determine physical compression ratio. Second difficulty is due to ground placement, which is independent of the element coordinate system. And this becomes a problem when the ground is defined as tensionist model. Due to independent ground placement, downward displacement can be compressional direction or tensile direction. The same is true of upward direction as well. As a result, WBB has the possibility to predict improper ground direction. The tunnel model using WBB is shown in this figure. Dashed gray line indicates the deformation shape. Considering the deformation shape, the loss of reaction is expected near the crown. However, due to the phenomenon, as I mentioned in previous slide, the ground reaction occurs in element B. This is wrong prediction. Thus, problem related to independent ground placement lead to incorrect solution, even not composite result. To solve the other problems, the process is proposed in my dissertation. This process is implemented within general finite element method framework. In the process, the key factor reference point and ground state function will be denote capital lambda. The detailed method used in the process are listed in the slide. The first set a reference point within the cavity, and using this point, the physical compression direction will be determined. After calculating the compression direction, check the agreement with physical compression direction and normal direction of the element. For example, the capital lambda is 1. Ground placement and element coordinate system is upper of the beam. And that is the upward direction in the element coordinate system that become compression. Using the collected retro displacement, ground stiffness and reaction are calculated. And this process can be excluded any improper prediction for ground reaction. To verify the proposed process, two WBB models are created. Difficulty of WBB is related to improper ground state. So tensionless hyperbolic model is used for ground. However, linear LC model is used for structure because the problem mentioned above is independent of the linearity of the beam. Note that the model A includes inversion problem only, like these model B is not. For reference, beam spring model is also created by using abacus. The abacus was selected due to providing nonlinear spring element. the result of all models are exactly same each other. Argument with result of model A and C indicate the accuracy of the WB model, as well argument with result of model A and B indicate the validity of the purpose process. Conclusion. This study provides finding of the numerical difficulty in WBB for non-flat period structure. It was pointed out that ground placement in WBB is independent of element coordinate system, and additional information should be given to determine the ground physical ground compression direction. Sorry. Also, the remedy of the problem is proposed within a general final element method framework. This study expands the WBB model to fully nonlinear analysis by combining layered section model. It also expanded this model for non-flat period structure. Thank you for listening.